Hi, welcome to the first short video of Unit 3 of Advanced in Organic Chemistry 2, which is devoted to the organometallic compounds of S and P metal groups. According to the syllabus of the course, we'll deal with the synthesis, structure, bond, reactivity, and applications of organometallics of group 1, mainly organolithium compounds, group 2, focusing on organomagnesium compounds, group 13, with organoboron and organoaluminium compounds, and finally group 14, centering our attention on organosilicon compounds. We will start with an overview, then we'll complete the synthesis of these compounds to go on with the structure and bonding, and to finish we'll address the reactivity and applications. The heavy alkali metals, potassium, rubidium, and cesium, form essentially ionic derivatives. These are extremely reactive. The alkyls of cesium are such strong bases that they can even deprotonate alkanes. Consequently, their organometallic chemistry is less developed than that of lithium and sodium. These last small electropositive metals enter into bridge bonding with organic groups. This property also extends in particular to beryllium and magnesium in group 2 and aluminium in group 13. Organomagnesium compounds, especially the Grignard reagents, play a key role in organic and organometallic synthesis. As you will study in organic chemistry, of particular value is their ability to add to polar groups such as the carbonyl and nitrile groups. Organoberyllium compounds have not found significant synthetic applications, largely because beryllium oxide formed by their combustion is extremely toxic. Even less is known of the organometallic chemistry of calcium, strontium, and barium. Although it's not included in the syllabus, we have talked about organozinc and organocadmium and organomercury compounds, which are still used in synthesis. Organic compounds of the elements in groups 1, 2, and 13 possess vacant valence orbitals and therefore are able to function as Lewis acids, forming adducts with electron pair donors, such as ethers, tertiary amines, and phosphanes. Regarding the synthesis of these organometallics, in Unit 2 we have just seen the main reactions we can use to form metal-carbon bonds. Remember, following the scheme that we have found in the book of Elsenbroich, we have named them direct synthesis, that is, the reaction of a metal and an organic alide, transmetallation, a metal and organometallic, or the reaction between two organometallics, and metallation, the deprotonation of an acidic organic compound by an organometallic compound. In this unit, we are also including the metal-halogen exchange reaction, which consists in the reaction of an organometallic and an organic alide. The reversible reaction is generally fast at or below room temperature. The equilibrium favors the formation of the lithium compound of the more electronegative organic group, which is the one which forms the more stable carbanion. Butyl lithium can thus be used as a source of aryl lithium compounds. Exchange is faster with aryl iodides than in chlorides and bromides. Let's go on with the structure and bonding. A wide range of structural types is found among the organometallic compounds of these metal groups. On one hand, the alkyls and aryls of the heavy alkali metals are essentially ionic. On the other hand, those of the least electropositive elements form covalently bonded monomers. For example, trialkyl boron and the dialkyls of zinc, cadmium, and mercury in group 12. Intermediate between these are the derivatives of lithium, beryllium, magnesium, and aluminium, which are associated through alkyl or aryl bridges. The cations of these lighter electropositive elements are highly polarizing, and the corresponding organometallic compounds have a tendency to form electron-deficient aggregates through alkyl or aryl bridges to give rise to oligomers, dimers, tetramers, hexamers, or polymers with multicentric electron-deficient covalent bonds. The description of the bond in this type of compounds cannot be done according to the classic scheme of 2 centers, 2 electrons, but in terms of the localized molecular orbitals. The highly polar character of organolithium compounds produces strong associations in solid state and in solution. The degree of clusterification of lithium alkyls varies with the nature of the solvent. In an alkyl lithium tetramer, the lithium atoms form a tetrahedral unit, while in the hexamer, the lithium atoms define an octahedron. The dialkyls and diaryls of beryllium and magnesium are generally associated. 2 coordination at magnesium in dialkyl magnesium is only observed in the solid state when the alkyl groups are especially bulky. In fact, they usually present a tetrahedral coordination with solvent molecules in the 3rd and 4th positions, and under certain conditions, the alkyl groups can act as a bridge between 2 magnesium atoms. Grignard reagents are also generally solvated with the magnesium center typically tetrahedrally sited, with the halide, the alkyl, and the solvent molecules, but also the halide can act as a bridge between 2 magnesium atoms. In boron organometallic monomers, the coordination number is mainly 3. When there is a hydrogen that is in alkyl hydrides, they form dimers that always exhibit hydride bridges rather than alkyl bridges. Organoaluminium compounds have a pronounced tendency to form dimeric units, but this association is hindered by bulky alkyl ligands. In organometallic compounds with multicentric electron-deficient covalent bonds, the description of the bond cannot be done according to the classic scheme of 2 centers, 2 electrons, but in terms of the localized molecular orbitals. To do it, let's focus on trimethylaluminium, which dimerizes as an example. Whereas the 4-terminal aluminium-carbon bonds have normal lengths 1.97 angstroms, the longer bridge aluminium-carbon bonds 2.14 angstroms are indicative of a lower bond order. As in the case of boranes, the aluminium-carbon-aluminium bridge may be described as a 2 electrons 3 centers bond by the interaction of one sp3 orbital of each bridging carbon with 2 aluminium sp3 orbitals. As each bridging methyl group and each aluminium contribute with 1 electron each, they furnishes a total of 4 electrons for bonding, and therefore 2 electrons are available for each aluminium-carbon-aluminium bridge, that is, 3 centers, 2 electrons. The bond angles and the aluminium-aluminium distance prompt a more refined interpretation, however. In particular, the short distance aluminium-aluminium 2.6 angstrom is indicative of a direct aluminium-aluminium interaction because it is almost the sum of the covalent radii of 2 aluminium atoms. In an extreme representation that involves an aluminium-aluminium bond and an sp2 hybridization of aluminium is assumed rather than sp3. Two characteristics that distinguish the organometallics of group 14 from those of group 13 are the lower polarity of the element carbon bond and, in compounds of the group 14, the presence of an octet configuration at the central atom. Consequently, the tetraalkyls of these group elements show no tendency to associate through 2 electron 3 centers alkyl or aryl bridges. They exhibit a tetrahedral configuration around the central element.